Every day, we perform a modern ritual. We tap the screen, select a private message or a sensitive photo, and we hit delete. We empty the trash bin. The icon clears. In that moment, we feel an immediate rush of relief, trusting that the information is destroyed. The device leaves the actual binary data untouched. It has simply removed the file's entry from the active registry, rendering it invisible to the user interface. This delete command is a high-level abstraction. It is an interface tool designed to bridge the gap between human expectations of privacy and the messy, permanent reality of the machine. To see why your data survives, we have to look past the glowing screen and descend into the hidden layers of the computing stack. The deception starts at the operating system. Erasing billions of microscopic ones and zeros takes significant processing power. To keep your phone responsive, the OS avoids the time-consuming task of physically scrubbing the drive. This animated diagram illustrates how your phone's storage functions like a massive library book. The OS maintains an index, vector lines mapping precisely where every file starts and ends. When you hit delete, the software takes a shortcut, severing the navigational line. By removing the pointer, the operating system labels that physical storage space as unallocated. It tells the phone that this exact spot is available to write new data over, eventually. Until new data arrives to physically overwrite those sectors, your sensitive document sits perfectly whole on the drive. It has simply lost its address. The problem deepens as we move away from the software, diving down into the physical silicon microchips powering modern smartphones. Solid-state drives use flash memory. While this technology is fast, it has a finite lifespan. The engineering techniques used to keep these chips healthy make absolute erasure a mechanical challenge. To prevent certain parts of the chip from wearing out faster than others, devices employ a process called wear leveling. This memory grid diagram shows wear leveling in action. The hardware fractures a single file into dozens of scattered pieces, distributing them across compartments. During a delete command, the central reference is cleared, but those scattered fragments are abandoned, remaining physically intact in isolated sectors. These fragments are invisible to your apps, but they remain readable to anyone utilizing digital forensic recovery tools. The hardware engineering designed to prolong your phone's life effectively preserves the ghosts of your data. Stepping far away from the local hardware, we finally encounter the macro-level architecture of modern computing, the cloud. Once a file syncs online, the power dynamic shifts. Deleting a photo becomes a request sent to a corporate entity, rather than a direct command to the storage medium. Most databases execute this request by flipping a visibility toggle. The file's status changes from visible to hidden on your dashboard, while the packet itself drops into a locked subtier. The actual asset stays preserved in deep corporate archives. It is logged and often absorbed into the massive datasets used to train artificial intelligence models. At the network level, erasure is replaced by an architecture of endless corporate retention. This brings us back to the surface, to that supposedly empty phone screen. The delete button reconciles the technical needs of efficiency and hardware longevity with our human desire for a clean slate. It simplifies a complex process of data abandonment into a comforting binary action. The technical reality remains. Once a piece of data enters the digital infrastructure, it becomes a permanent part of that infrastructure. Digital autonomy requires acknowledging this physical permanence. True control starts with understanding that the storage chips and server racks we rely on are built to remember, not to forget. Think twice before you hit send or save a file, because the digital footprint you leave behind is permanent.